Right, so section 10.3 of chapter 10 introduces you to the Newton-Raphson method of finding a solution to an equation, like I said before, that otherwise would be difficult to solve. So this is the formula that you are going to be using. It's really simple to use, and it's always the same. It has got the derivative in the denominator of that part, so that's f dash of xn, and the function on the top, and you've got x minus the quotient as written here. Now, where does it come from? It's simply gives you an idea of starting from a point on the curve, and then you are finding the equation of the tangent at that particular point. And then as soon as you find the equation of the tangent, that formula helps you evaluate this value, because the equation, so you find it where it crosses the x-axis by making y equals 0, and then by using it again, you're going to use this particular values, which will become your x1, and then you're going to find tangent, there you go, at the point with that x coordinate, and then you could see that those tangents get closer and closer to the point of intersection. Okay, how does it work? So imagine starting with the first one over here, so x0. Let's find the equation of that tangent, and let's use it to find the value of x1. So look at this very carefully. You can generalize it for xn, but let's just use x0 and x1. So the tangent has the following equation. So remember, you need the gradient and you need a point. We've got the point. So the point is x0 and f of x0. And we need the gradient. The gradient is simply the value of the derivative of the curve at that point. So the gradient of the tangent is always f dash of x0 in this instance. Let's put it into the equation. So y minus the y coordinate, which is f of x0, equals m, so f dash of x0, and then x minus the x coordinate. Now the idea is to find the value of x. Now x here is going to be x1 and y is going to be 0, because we are now using that tangent over here, the equation of that blue tangent over here, to find where it intersects the x-axis. So where does it intersect the x-axis? At point x1, 0. So let's substitute these into the equations. So you've got y is going to be 0, and then x is going to be x1. So you've got 0 minus f of x0 is equal to f dash of x0, and then x is x1. All we need to do is just rearrange it. So the first thing I'm going to do is divide by f dash of x0, so the gradient, so f of x0 over the gradient. And you've got x1 minus x0, and we want to find x1, so let's move that x minus x0 across, becomes positive. And you do obtain the first iterative formula for that particular instance. But if you had in general, then you would have xn plus 1. You get xn minus f of xn over f dash of xn. There you go. So that's a nice nice formula. It's really, really powerful. There are some situations where it doesn't work, so we'll look at those in more detail, just to give you a bit of an idea of when it doesn't work. Okay, so you could have a curve. Let's sketch it over here, something like this. Okay, now imagine you are going to this point over here, and you are using the Newton-Raphson method. So effectively you are looking for a tangent. Now if you've got that tangent, it's going to be horizontal. So at the minimum point or maximum point, the tangent is horizontal. It will never cross the x-axis, so you won't be able to use the Newton-Raphson method. This could also be happening close to those points, so where the flatter the tangent, the further away from the solutions you could get. Doesn't mean it won't always work, because it could come back, but it is a possibility. Okay, so it's a bit more temperamental then. So let's have a look at the examples that follow this section. So in the example 6, we've got another cubic. It's been sketched for you, and f of x z equals 0 has a root alpha in the interval between 1.8 and 1.9. So we are told this, we don't need to show it. Explain why at this particular point, so marked on the graph as it's the minimum point, clearly x0 equals to p is not suitable. And as I said to you before in my example that I've drawn just before this one, is you can't have the horizontal tangent. And if you directly refer to the formula, you could see that over here that we are going to be dividing by the gradient 0. So here f of p is equal to f dash of p is equal to 0. We cannot divide by 0, but I wouldn't just say that. So could not be equal to 0, so you can't use that. But I wouldn't just leave it there. I would definitely say tangent is horizontal. So tangent at x equals to p, so at a, is horizontal. Therefore does not cross the x-axis, and that's what you're relying on, and you might need to put it in your explanation. Okay, so the next section, we've got to use x of 0 equals 2, and we've been asked to carry out Newton-Raphson iteration twice. You'll be told how many times to use it, so read it very carefully. So they could call this as the first approximation, and they will say find the next two approximations. So first of all, we've got to differentiate the function, so we need the derivative. So it's going to be 3x squared at 4x minus 5. And let's find the values. You can it's absolutely fine to put everything into the formula and then put the value in with using the calculator, especially as you need to do it twice. Okay, or you can evaluate them separately. So you could find f of dash of starting with 2. So we're going to 3 times 2 squared plus 4 times 2 minus 5, which is 3 times 2 squared plus 8 minus 5. That's 15. We are going to find f of 2 as well. So put 2 into this equation, 2 cubed plus 2 times 2 squared, so that's 16, minus 10, so that's 6, and minus 4, that should be 2. And then you sub it into the formula. So x1 is going to be equal to 2 minus f of 2 over f dash of 2, which is 2 minus 2 over 15, which is going to be 28 over 15. So with what I would do though, I would definitely do it myself in the following way. So I would write it as x of n minus, and then over here I would write the formula for the function x n cubed plus 2xn squared minus 5xn minus 4, and in the denominator the derivative, so 3xn squared plus 4xn minus 5, and then use that with x0. Just write this way. You can even substitute it with 2 if you want to, but use your calculator to find that. So we are going to use ans minus, and let's put the whole function using ans key. It's worth doing it because I think I put it squared, because you could make a mistake and you're going to do it twice. So ans to the power of 3 plus 2 ans squared minus 5 ans minus 4. In the bottom of the fraction we're going to put the derivative, so 3 ans squared plus 4 ans minus 5. Okay, I don't think I've put 2 in, so that's fine. Let's just go back. 2 equals okay, so that's 28 over 15. Write it as a fraction, write it as a decimal. Looks like it's recurring. So they probably ask you to give your answers to 4 decimal places, or sometimes 5. So 4 decimal places is this one. Now to achieve the second approximation, or the third if you call the number 2 as the first, press equals. Okay, so that gives me, and again, if you want to show that you are putting x1 in, you can copy that down, it's fine. You know, I've shown my derivative. You need to show that you've differentiated. You can't use the derivative function on the calculator. So this is 1.85584, which rounds to 1.8558 if you use the 2 4 decimal places, for example. Might be 3 decimal places. I'm not sure what. Actually, let's just double check. In this particular question, actually they've asked us to do it to 3 decimal places, so this one is going to be 1.867, and this one to 3 decimal places, 1.856. So that's my answer, to 3 decimal places. Okay, in part C, you've been asked to show that the solution is, let me just double check, by considering the change of sign in f of x, we are going to show that the solution is actually accurate to 3 decimal places. So we are going to write let alpha is 1.856. If it's correct to 3 decimal places, what you need to show that there is a change of sign using the bounds. That's what I tend to use. So we're going to use the upper bound 1.8565, and we're going to sub it into our function, and we're going to use the lower bound, so 1.855, and then 5. Yeah. Okay, so we're going to sub these in. So testing that these agree, anything between those 2 values will round to 1.856. Okay, so Have I got the function somewhere there? Still typed in? No. Okay, so let's pop it in. And cubed plus 2 and squared minus 5 and minus 4. Okay, so let's set 1.855. Up. Okay, that gives me the value of minus 3.475 times 10 to the power of minus 3. Write it properly, don't miss out that standard form. And then put 1.8565 equals, scroll up, equals again. That gives me 9.28 times 10 to the power of minus 3 again. That's greater than 0, that's less than 0. So f of x is continuous and sign change. Therefore, alpha is equal to 1.856, correct to 3 decimal places, because you're using this to prove that it's correct to 3 decimal places. Okay, that takes us to exercise 10.c, 10C, so please have a go at all the questions in this exercise.